Hello, everybody, and welcome to Copper Cable Testing and Troubleshooting. I'm your presenter, Chris Pawelko. In this presentation, we're going to talk about the importance of testing and troubleshooting copper cables. Then we're going to get into essentially two different subcategories with regards to testing copper cables: physical troubleshooting and performance issues. So why is it important to test and troubleshoot copper cables? Well, let's kind of deviate a little ways away from copper cables, and let's envision this car that we see here. This is the Bugatti Chiron. It has a top speed of 420 kilometers per hour. Now, if we were to take that car that's capable of going 420 kilometers per hour, and we were running it on this particular road that we see here, we're not going to get 420 kilometers per hour. We'll probably get a top speed of probably less than 1 kilometer per hour on a road that's similar to this. So shifting gears back to copper cables, yes, pardon me for the pun, but today's copper cabling has high-speed applications. We've had 1 gigabit per second applications for many years now, but now we're going up to beyond that. So we can go 10, 25, and even 40 gigabit per second services over this copper infrastructure. And if we do take a look at copper cables, 80% of the networking issues reside in the physical layer. Copper cabling is the most physically exposed portion of your network. So you're going to see patch cords across desks, across floors, stretching down from ceilings, all those different places. It's very important to A, get your infrastructure done correctly, and B, to test and troubleshoot your copper cable for optimal performance. Now, if we take a look at cable faults, copper cable faults comes in two different categories. So there's the physical faults and the performance faults. Physical faults are what I call hard faults. They're the most common set of faults in structured cabling, and we can break this category down into two different types of tests for this category of faults. So we're going to take a look at wire mapping and length measurements. Wire map is a type of a continuity test, and it checks to ensure that all the wires in the cable are connected properly. So some of the testers that you're going to see for this can range from very inexpensive wire mappers using such things as LEDs to certification testers that have the ability to perform a wire map test. The first wire map fault that we're going to investigate are opens. Opens are when a wire is not providing continuity. So if we take a look at this picture here, we see that pin number 2 has an open in it. So it's not providing continuity from side 1 to side 2. A wire map opens test checks to ensure that all the wires in the cable are connected properly. Now, some testers will check for shield continuity. So some copper cables do have grounded shields on them. And so some of these testers will actually check to make sure that the shield has continuity on it. Now, when it comes to opens faults, they're caused by damage to the cable, improper termination, or if you do have faulty connectors or jack. Now, the next wire map fault that we're going to investigate are shorts. Shorts happens when two wires are connected to each other. This causes a direct electrical path from one wire to another. Now, shorts are caused by damage to the insulation on wires, causing a metal-on-metal connection, an improper termination, faulty connector or jacks, and or damage to the cable by such things as nails or screws. The next wire map fault we're going to talk about are miswires or miswired. Miswired is when wires are not connected to the corresponding pinouts. Miswires are caused by improper termination, and in some cases they could be caused by faulty connectors themselves. So a word of caution when it comes to miswires. There are some miswires that might look like they've been connected improperly, but they're intended to be this way. So we have 3 examples here. The first example is a Cisco rollover cable. Now this particular cable is used for serial connections onto a Cisco device. The next one is a 100 base TX crossover cable. And the last one is a 1000 base T crossover cable. Now, crossover cables are used in networking to connect a PC to another PC or in older switch equipment from one switch to another. Now, the next one we're going to talk about kind of crosses the line between performance faults and physical faults, and they're called split pairs. So split pairs occur when a wire from one pair is providing continuity for the one wire of another pair. Split pairs cause massive, and I mean massive amounts of crosstalk. So you will also get near-end crosstalk failures, and all the associated crosstalk tests will fail that particular test. Wire map testers cannot detect split pairs. This is a test that requires the ability for the tester to test for crosstalk. Wire map testers themselves will actually show that there is continuity, but there's a major fault with regards to crosstalk. So keep that in mind. Your normal wire map testers will not show a split pair fault unless it does have the technology in order to detect crosstalk. Now, split pairs are always caused by improper termination. This has nothing to do with the cable or connectors, or it has to do with how the cable was terminated. Now we're going to move on to length. Length measurements are the most basic of the copper cable tests. So all categories of testers will have the ability to measure length in one way, shape, or form. Now, length is measured in two ways. It can be done by a capacitance measurement or use time domain reflectometry technology. Now, if we do take a look at the capacitance type of length measurements, capacitance measurements were first used to measure the length of a cable. Each different type of copper cable, so for example, category 3 would have a specific capacitance per meter. And the formula for this is the length is equal to the capacitance per unit length divided by the total capacitance. Now, the drawback to using capacitance is that it's not as accurate as time domain reflectometry. Now, the time domain reflectometry, so we are going to refer to it as a TDR. And what happens is that a pulse is sent down the cable, and when it meets a high impedance event, such as an open, the signal reflects back to the meter. When the meter injects a signal, it times how long it takes for the signal to reflect back and then does the calculations. All right, so now we're going to progress forward to performance issues. So performance issues are more complex than the physical tests that we just seen over the last previous slides. These tests do require the measurements to be done by frequency, with the exception of propagation delay and delay skew. The test needs to have specialized equipment in order to perform these tests. So our wire map testers, the inexpensive ones, cannot do these types of tests. So many of these testers are very expensive. These tests are also needed in order to certify the cable in accordance with various different standards. So the different standards bodies such as the TIA do require these particular testers and these particular tests to be performed in order to certify that particular cable to their specifications. Now, the first one that we're going to take a look at is propagation delay. So what propagation delay is the measurement of how long it takes a signal to go from one end of the cable to the other. And this value is measured in nanoseconds. Now, you might take a look at the results and you'll say, hey, wait a minute, why are they all different? Well, the measurements within the cable will be different due to the different twist ratios within the twisted pair cable itself. Now, if you do run into any problems with regards to propagation delay or if it fails, the number one cause for this is the length of the cable. So check the length of the cable to ensure that it is not too long. Along with propagation delay, delay skew goes hand in hand. A little bit of a background on delay skew. So all four pairs in a cable that we're using today for applications such as gigabit Ethernet, all four pairs are transmitting and receiving at the same time. In order to maintain timing, there needs to be a window when the signal arrives at the receiving end. This is called delay skew, and it is measured in nanoseconds, and the values will be different based upon pair to pair due to the different twist ratios inside the cables themselves. To troubleshoot delay skew is exactly the same as propagation delay. You have to check the length of the cable because it is dependent upon the length of the cable. Now we're going to talk about insertion loss. Now insertion loss, it was previously known as attenuation, and it is the amount of loss of an injected signal as it travels from one end of the cable to another, and it is measured based upon frequency. The units of measurement for insertion loss are decibels or dBs, and you want to have a smaller dB value because a smaller dB value means you have less loss, less insertion loss as you go down the cable. And to troubleshoot insertion loss failures, the very first one is length of the cable. If your cable is too long, then it could fail insertion loss. You can also look at port connector and jack terminations. And last but not least, higher temperatures do cause insertion loss in cable. So now we're going to talk about crosstalk failures. Crosstalk is the coupling of a signal from one wire pair to another. It is one of the major causes of performance issues with copper cable. And this doesn't matter if you are using 4 pair, 25 pair, 100, 600, and so on and so forth. The best way to describe crosstalk is back in the old days when you used to make a phone call and you would actually hear faintly another voice on the line. So that is crosstalk. And the causes of crosstalk are wire pairs becoming untwisted, because the twisting in the wires are there to mitigate crosstalk. So if they come undone, then it's going to cause crosstalk. Plus also improper category components. So say, for example, you have category 6 connectors and you have category 5E cable, and then you go to test at category 6. You will have crosstalk issues. Crosstalk, the measurements are based upon frequency, and they're measured in units of decibels. Here's the important note about crosstalk. The higher dB value, the better the performance is. Because if we take a look at what really is being measured is the mitigation of the crosstalk from the leaking pair to the victim pair. So we're measuring really from the victim pair to see how good it can mitigate that crosstalk. Now, there are a couple of different terms when it comes to crosstalk. And the two terms that we're going to talk about are near-end crosstalk, which is the coupled signal from the source that returns back to the source. So that's what is called near-end. And then there's far-end crosstalk, which is a coupled signal from the source, which is coupled into the adjacent wire pairs. But then that coupled signal continues to travel down in the direction of the destination on the victim wires. As I mentioned before, crosstalk measurements need specialized testers. And these testers are not cheap testers because they do require specialized circuitry and programming in order to detect crosstalk. But also many of these testers do have tools to help you discover where crosstalk failures are. And here's an example of one of those types of tools to help you find where crosstalk is. And the best thing to remember when it comes to these types of tools is good crosstalk performance will essentially have a straight line. So you do not want to have any crosstalk. Now, in this particular example, you do see some bumps located here and located here. Those are your connectors. Anytime that you do any untwisting of your wires, you're going to get some crosstalk. And so at your connectors, in order for you to terminate them into the housings themselves, you do have to untwist those wires just slightly. Some of these testers are so sensitive that it will actually detect that. Now, you do want to make sure that you have as close to a flat line as possible. So let's take a look at a sample of a bad crosstalk performance. So a couple of places that we see here on this particular tester. Now this particular test is using the Fluke Networks high definition time domain crosstalk analyzer. So there's a couple of really bad spots on this particular test result. So the first one we see here is right here. So what that is, that's a bad connector. So the connector is so bad that it goes off the scale of this particular test. So the first thing you want to do is you want to check that termination to make sure that everything is fine, which I can tell you right now, everything is not fine. The next thing you want to take a look at is on the cable itself. So if we look in this segment here, we notice that there's a lot of bumps there. Remember, we want to have a straight line. With these bumps here, we can tell there are problems with this particular cable. Now, in this scenario, this particular cable could be a lower category type cable. And then last but not least, if we look at the far end connector, we do see some issues that are happening here. So with regards to this particular type of test, we could turn around and look at the different colors and say, hey, you know what? The terminations on 3, 6, 7, and 8 are the issues. But in all honesty, you would want to go back in and re-terminate that connector. Now, the next performance issue that we're going to talk about is return loss. Now, return loss are losses due to signal reflection due to impedance anomalies in the cable. So the major causes for this are damaged cables in areas where there was crunching of the cables due to such things as cable ties. Plastic cable ties are not the friend of high-performing cables. So it's very important to ensure that you do not, if you are using plastic cable ties, that you do not have them way too tight. But there can also be damage inside the cable as well from excessive bends or anything else that does damage or change the twist ratios inside the cable. You can also as well have improper category components. So this is similar to near and crosstalk. The measurements are based upon frequency. The units are decibels or dBs. As the same as near and crosstalk, the higher values you have, the higher dB values you have, the better the performance with regards to return loss is. Now, many testers out there do have tools to help you locate where the problems are with regards to return loss. So return loss measurements do need the specialized testers, and many of these testers do help discover where those crosstalk failures are. What you want to see when it comes to return loss, you want to see a straight line. So this particular tester that we're using a Fluke Networks tester. So they have the high definition time domain reflectometer. And ultimately, you still want to have a flat line. Now, if we do take a look, we could see the connectors here. And so because we had to untwist some of the wires, there will be some impedance anomalies. So it will show up, but ultimately you want it as close to a flat line as possible. So we're going to take a look now at an example of a bad return loss performance. So in this particular trace, what we see is we've got some bad connectors here. So anytime that you have the twists change or you have to undo any untwist, this is where you can have return loss failures. Now you can also have return loss failures inside of a cable. And so what it would be would look something similar to this. So if you do see something similar to this, then what that is an indication of is that there is an impedance anomaly at that particular location. So for troubleshooting, you want to check your terminations. So anywhere where you have your wires becoming untwisted, you want to check your cable for any damage. You also want to look for plastic cable ties. So plastic cable ties are really good, but if you pull on them too tight, then they can cause damage to the cable and may cause return loss failures. And as well, mixing different category components together. Now, one last thing before we leave today is to talk about with regards to return loss is the 3 dB rule. Now, in the TIA 568 standards, there is a rule called the 3 dB rule. So what the 3 dB rule is wherever the insertion loss value is below 3 dB, return loss is not required to be reported. So many testers out there will still report it as information only if it meets this criteria. So let's take a look at an example of the 3 dB rule. So this particular chart here, we can see that the 3 dB value has been reached at 85.250 megahertz. And if we look at the return loss measurements, we can see that there is a gray line here. And so that gray line represents that those values are information only. So they're not required to be reported by the standards. And so then the red line going beyond that shows that those values are reported in accordance with the standard that has been selected. Thank you for joining us today. Visit yournetworkexpert.com for the latest articles and resources to help you further understand structured cabling and networking. As well, visit our YouTube page and click subscribe to get the latest videos from Your Network Expert. Thanks for watching. See you soon.